order to perform analysis on this aluminum fin tube, I have opened Ansys Workbench and I am going to take this steady state thermal, place it on the project schematic. And now I am going to double click on the engineering data, go to engineering data sources, then go to general materials library. In the general materials library, I am going to select this particular aluminum alloy and add it to my present analysis. And once I have done this, I am going to close the engineering data. Then I am going to right click on the geometry cell, go to import geometry, go to browse, and I am going to select this particular fin tube and I am going to open it. And once I have imported the geometry, I am going to double click on the model cell in order to open this Ansys mechanical to perform the further analysis. Here there is a special requirement that we should be applying not a uniform temperature, but we should be applying a uniformly varying temperature on the interior face of this particular fin tube. So this can be done through equations. So we are going to see how we can apply that equation. So once this particular geometry has opened, I am going to go to the geometry and I am going to just change it from the structure steel to the aluminum alloy. So once I change the material assignment, now I am going to just right click, say mesh. So once I generate the mesh, then we are going to apply the boundary condition. The first boundary condition is the temperature, and that too uniformly varying temperature. As specified in the problem, what happens at this starting, the temperature is around 200 degrees. At this particular exit, the temperature is around 150 degrees and it is uniformly varying along this particular length. So what happens, we need to be simulating that particular condition. So in order to apply the temperature, right now what I am going to do is I am going to right click, say insert, go to the temperature boundary condition, and I am going to select this particular interior face. And once I select this particular interior face, I am going to apply it in the geometry selection. And now here if I enter the value, it will be a constant value across this particular face. But what do I want is the uniformly varying temperature which starts at 200 here and which ends at 150 degrees at this particular end. For that purpose, what I am going to do is I am going to change this from constant to function. And once I change it to function, then I need to give the function value. The function value is 200 minus 0.25 into y, and this particular y ranges anywhere from 0 to 200. Okay, so what happens if this y is 0, then 200 minus 0.25 into 0, the temperature will become 200. Likewise, if the y is 200, 200 minus 0.25 into 200, which means 200 minus 50, it will become 150 degrees. So this is how you can apply uniformly varying temperature. If in the case of a structural analysis, you can use the same equations to apply uniformly varying loads on different structures. And once the temperature is applied, then we need to give the convective boundary condition. Here we need to give the convection, which is a temperature dependent property for this particular problem. For that, what I am going to do is I am going to right click, say insert, go to convection boundary condition, and first of all let me select all the outer faces so that I can apply the convection boundary condition. So once I have selected all these particular exterior faces, now what I am going to do is I am going to select apply, and once I select apply, now I am going to, instead of giving the film coefficient as a constant, I am going to change it to tabular. And once I change it to tabular, here in the tabular data it is asking us what is the independent variable. Here for this particular problem, the independent variable is the temperature. So I am going to select temperature. So once I select the temperature, here see a table has been updated. Here we need to give the temperature, and based upon the temperature we have given in this particular column, we need to give the convective coefficient. So at 0 degrees the convective coefficient is 0.04. Then at 10 degrees it is 0.054, and at 20 degrees this particular convective coefficient is 0.06. Likewise at 40 degrees it is 0.066. Sorry, it is 0.066. and then at 60 degrees it is 0.0007, and at finally 100 degrees centigrade it is 0.0077. So this is how our convective film coefficient is going to vary with the temperature. So here you can see the variation of this convective film coefficient with respect to temperature. So once we have given all this convection condition and temperature, we are going to right click and say solve. So before going to solve, I need to define this say ambient temperature as well. The ambient temperature is around 20 degrees. So I'm going to give 20 degrees ambient temperature, and I'm going to right click, say solve. Once I solve this particular problem, I'm going to just right click, say insert, go to thermal, and I'm going to select the temperature, and I'm going to say evaluate all results, and I'm able to see the temperature distribution inside this aluminum fin tube. Likewise, see for example, if I am going to right click and say insert and go to this thermal and go to directional heat flux, I can select this particular surface, or otherwise I will leave it to all bodies, and I'm going to just right click, say evaluate all results. I can see the heat flux through every surface of this particular aluminum fin tube. So this is how you can solve aluminum fin tube problems or convection heat transfer mode problems using Ansys mechanical or Ansys Workbench. In the next lecture, we are going to see how to model the radiation mode of heat transfer using Ansys Workbench.